Dear students, in this video, we will discuss the stereochemistry of SN reactions. Okay? So, please watch the previous videos wherein we discuss the details of SN1 and SN2 reactions. Now, stereochemistry plays a very important role in the especially in the pharmaceutical industry. That will be discussed to some extent while we go ahead with our discussion. Okay, now before we get into the stereochemistry of SN reactions, I have classified this discussion into two parts, wherein part 1 is the basics of optical isomerism. Alright, now before I go to optical isomerism, let me make you recollect about isomerism. You have learned in class 11 that isomers are compounds with the same molecular formula but different properties. Now this difference in properties arise due to, now comes the two types of isomerism. One is structural isomerism and the other is stereoisomerism. You learnt in detail about structural isomerism also in class 11, right? The chain, position, functional group isomerism, etc. You also learnt about stereoisomerism. So in structural isomerism, the compounds had the same molecular formula but different structures. Whereas in stereoisomerism, compounds have the same molecular formula, same structures but different spatial arrangements. Okay? In that category, you have geometrical isomerism as well as optical isomerism. You also learnt about geometrical isomerism in the chapter hydrocarbons of class 11. Alright, so here we are going to focus on optical isomerism, which is a type of stereoisomerism, a special type of stereoisomerism which talks about non-superimposable mirror images. Now what do we mean by non-superimposable mirror images? Simple example, the learning of this concept started with the palms, okay? Our palms, the left palm and the right palm, they look like mirror images, alright? So imagine a plain mirror between the left and the right palm, they look like mirror images, okay? Now I'm trying to superimpose my right palm on the left palm. This is called superimposition, not this, okay? So I'm trying to superimpose the right palm on the left palm and I notice that the two palms are not superimposable, alright? So this was studied initially and the word handedness was the point used, okay, was a concept used, and the handedness has a Greek name called chier, C-H-I-E-R. So such compounds or such substances need not be compounds, objects which are non-superimposable mirror images of one another were called chiral objects, named after chier, handedness in Greek. Alright, so chiral objects. So we have two types of objects, chiral objects and achiral objects. So we'll first look at objects and then we will look at compounds. Okay, so what are the other examples of chiral objects? So what I mean by chiral objects is non-superimposable mirror images. Alright, that means images are not identical. They look identical but you cannot superimpose them. Okay, for example, this is what I've shown as a left hand, right hand. Cannot be superimposed. You take a conical flask, place a plain mirror, look at the mirror image. You can superimpose the two conical flasks. Okay, so this is not chiral. It's called achiral, an achiral object. Okay, which means the two mirror images can be superimposed. That means they are identical. They have absolutely no difference in their properties. Alright, now another typical representation is that of this again, representation of the palm and the reflection on the plane mirror. They are mirror images which are non-superimposable, so chiral. But look at the chair. The image of the chair, mirror image of the chair can be superimposed on this and therefore it is an achiral object. Spoons, two spoons are achiral object. But what about a pair of shoes, a left shoe and a right shoe, right? So they are non-superimposable objects, alright? So a pair of scissors, a pair of socks, all these are typical examples of chiral objects, okay? You cannot insert your right foot into your left shoe and vice versa. So that's why a pair of socks is also an example of a chiral object. So that's the general idea about a chiral object and achiral object. Okay. Now, so that is about chiral and achiral. So that has been discussed. So chiral means objects whose mirror images are non-superimposable. Achiral implies whose mirror images are superimposable, and we have seen some examples. Okay. Now we have to identify what is that structural requirement. Now let us come to a compound, not object. Okay. So what is the structural feature in a compound responsible for it to behave as a chiral compound, wherein its the mirror images are not superimposable. Okay. So any compound with a chiral carbon or an asymmetric carbon will show chiral behavior. Okay. Now what do you mean by a chiral carbon or an asymmetric carbon? This is nothing but a carbon atom bonded to 4 different groups. Okay. In general, if I write A, B, C, D, alright, A, B, C, D. Now this carbon atom is a chiral carbon normally represented by an asterisk. For example, if I write a structure like this, CH3, CHOH, COOH, formula of lactic acid. Okay, so focus on this carbon atom. This carbon atom. This carbon atom is bonded to a methyl group, an OH group, a hydrogen and a carboxylic acid. So this carbon atom is bonded to 4 different groups. Need not be atoms alone, 4 different groups. Therefore, this carbon atom is a chiral carbon or an asymmetric carbon. Okay, so compounds which possess an asymmetric carbon or a chiral carbon will show optical isomerism, but there are exceptions which is not required to be discussed here. Now let me explain this by using a model. Look at this. The black one at the center, the central carbon atom or the asymmetric carbon atom, because it is bonded to 4 different groups. The 4 different groups are represented by 4 different colors. Okay, so this is representing a chiral carbon or an asymmetric carbon. Alright, let's construct its mirror image. So here I have the mirror image. Look at the mirror image. Okay, so these two are mirror images of one another. Let's see if they can be superimposed. Okay, so what do? I place this on this, and I notice that the blue and the orange are superimposed, but the green and the purple are not superimposed. In other words, this mirror image is not superimposable on this. So this is a typical representation of a pair of mirror images which are non-superimposable on one another because of the presence of a chiral carbon. Now look at this structure. In this structure, you notice that the central carbon atom is bonded to 2 identical groups. So out of the 4 bonds, 2 are different, 3 are different, but the 3rd and the 4th are identical. Let's see what happens to its mirror image and whether the mirror image can be superimposed on this. Okay, so here, this is the mirror image of this, right? This is the mirror image. Okay, so I'm trying to superimpose this on this. At one glance, you notice that they cannot be superimposed because the green and the purple are not superimposable. But if I rotate it through this angle, all the groups are superimposed. You notice that? The 2 reds, the 2 greens, the 2 purple, they're all superimposed. So what does that mean? If the central carbon atom is not asymmetric, not chiral, the mirror images can be superimposed. Okay, so no optical isomerism is observed here. So whatever I demonstrated is right here. Now this is your chiral carbon, 4 different colors, and this is the mirror image, and you notice that the mirror image cannot be superimposed on this. So non-superimposable mirror images. Alright. Now you notice that in this representation, 2 colors are identical. Now these are the 2 mirror images. Okay, so if this mirror image is rotated through an angle of 180, you get this. And if you try to place this on the first one, they are found to be superimposable. Okay, hence this is not a representation of a pair of optical isomers. Alright, I hope it's clear to you. Now let's go back to the discussion, back to a chiral compound. Alright, so we know that you have a compound and its non-superimposable mirror image. Both of them are optical isomers or enantiomers of one another. Now both these mirror images obviously have the same structure. So we don't expect significant differences in their properties. They're both found to have the same melting point, boiling point, etc. Alright, but they do differ in certain special properties, and one such property is called the optical activity. Now what is optical activity? To understand what optical activity is about, we first have to understand what is meant by a plane polarized light. Okay? Now, ordinary light vibrates in all the planes. This is how an ordinary light looks. Vibrates in all planes. Okay? A plane polarized light is one which vibrates only in one plane. So this is a plane polarized light. So when you pass ordinary light through a polarizer, it gets converted to a plane polarized light. Now what happens? Optical activity is the ability of a compound to rotate the plane of plane polarized light either in the clockwise direction or in the anti-clockwise direction through a specific angle. So what we notice is, out of the two mirror images, non-superimposable mirror images, which are the optical isomers, one optical isomer will rotate the plane of plane polarized light to the right or in the clockwise direction. The other isomer, the other optical isomer, will rotate the plane of plane polarized light in the opposite direction, to the left or in the anti-clockwise direction through the same angle. So that phenomenon is what is known as optical activity. Okay? Now to understand what optical activity is, an experiment called polarimetry is done. And polarimetry is done using a device or a setup of apparatus called polarimeter. A polarimeter. It is a set of many devices. Let's see how a polarimeter works. Now these are the various components used in a polarimeter. Okay? Sodium lamp plays the role as the source of light. Okay? So the ordinary light vibrating in all planes is passed through a polarizer and is converted to a plane polarized light. Alright? Now this is what is known as a sample tube. So in this sample tube, we take one optical isomer. So one of the mirror images. Okay? One of the two optical isomers, we place the solution, aqueous solution of that optical isomer is placed in this sample tube. Now there is a protractor here which measures the angle of rotation. Alright? Now what you notice is, when the plane polarized light passes through the solution, the molecules of that optical isomer will rotate its plane in the clockwise direction. See, this was your plane polarized light. Now what comes out is this. The plane polarized light has been, the plane of the plane polarized light has been rotated to the right in the clockwise direction. See, in the clockwise direction to the right through a specific angle which is measured here. Alright. Now this clockwise rotation or this rotation to the right of the plane of plane polarized light is called dextrorotation, and this isomer taken in the sample tube which is responsible for this dextrorotation is called the dextrorotatory isomer. Now if you replace the substance solution in the sample tube with the other isomer, the mirror image, the non-superimposable mirror image, alright, this is the plane polarized light. When this plane polarized light is passed through the sample tube containing solution of the other optical isomer, the non-superimposable mirror image, what you get is this. The plane polarized light has been rotated to the left or in the anti-clockwise direction. Now this type of optical activity is called levorotation, and that isomer is supposed to be was referred to as levorotatory isomer. Alright, so let's go back to our discussion. Now optical activity results in one of the two isomers rotating the plane of plane polarized light to the right and is called the dextrorotatory isomer, represented by D or plus, not capital D, small d. The other isomer, its non-superimposable mirror image, rotates the plane of plane polarized light to the left through the same angle and is called the levorotatory isomer, represented by L or minus. Okay, so these are the two. So in this manner, the two optical isomers differ from one another in their optical activity. One is dextro, the other is levo. Alright, now let's see how to represent a pair of enantiomers or a pair of optical isomers. Right, let's take the example of lactic acid or any other compound. Let's take the example of CH3COOH, COOH, or we can have C2H5. So it's not lactic acid, another compound. Alright, this is 1, 2, 3, butan 2-ol. Okay, now look out whether there is an asymmetric carbon or a chiral carbon in this compound. So you notice that this carbon atom is asymmetric, bonded to 4 different groups: a methyl, a hydrogen, a OH, and a C2H5 group. Okay, let's now represent it by the wedge and the dash representations. Alright, so we have the carbon atom. Okay, so we have the two solid lines, a dash and the wedge. Alright, we place a plane mirror here and its mirror image will have the bonds in this manner. This, the dotted line and the wedge. Okay, now we can place the groups in any which way you want in structure 1. This is structure 2. Okay, so in this structure 1, suppose I place hydrogen here, the OH here, CH3 here and C2H5 here. Its mirror image will look like OH here, this is CH3, this is C2H5 and this is hydrogen. This is how you represent a pair of enantiomers. Whatever groups you fix here, the same groups have to be fixed in the mirror image. The same arrangement has to be done here in the form of a reflection or mirror image. Let's have a look at this. See, these two are examples. 2-bromo-butane. This is the chiral carbon. So these are the two structures, structure 1 and structure 2. Right? And if they differ from one another in their optical activity, if any one of them is dextrorotatory, the other will be levorotatory or vice versa. Alright? So that is about the representation of enantiomers. Now what is a racemic mixture? Alright? A racemic mixture is an equimolar mixture of the D and L forms. So 50% of D, the first isomer, and 50% of L. Alright? This mixture is referred to as a racemic mixture. Equal amounts or equal concentrations of the two optical isomers, the two non-superimposable mirror images. Now when I subject this mixture to the polarimetric experiment or to a polarimeter, alright, the plane polarized light is made to pass through a sample tube. Now this is our sample tube. Let the sample tube contain 50% of the D isomer, the first optical isomer, and 50% of the levorotatory isomer. So what happens is, the plane of this plane polarized light will be rotated to the clockwise direction by 50% of the dextroform, and the plane of the plane polarized light will be rotated to the anti-clockwise direction by the remaining 50% of the levorotatory form. So what happens is, the two opposite rotations get cancelled out. This is called external compensation. And what happens to the plane polarized light is, it comes out as a light without having undergone any rotation. In other words, a racemic mixture is optically inactive because the plane of plane polarized light does not undergo any rotation when passed through a racemic mixture solution. Okay, so racemic mixture, the discussion of racemic mixture is extremely important again, especially in the pharmaceutical industry. So you have the plus and the minus forms. Most medicines that are available in the market are racemic mixtures. Alright, you have the equal amounts of the plus and the minus forms. Sometimes it is quite dangerous to use a combination of both plus and the minus forms, and this you will understand when you do some research and learn about the thalidomide tragedy that occurred in 1960s. That is something that you can Google and get information about. So after that tragedy, a racemic mixture was subjected to resolution. A racemic mixture was separated to give you the D isomer and the L isomer, because even though they have similar properties in the form of melting point and boiling point, they differ in their optical activities. Most of their chemical properties are same. But when the D and the L isomers are made to react with another chiral compound, both of them show different properties. Okay, now a simple explanation or example of that can be illustrated by this compound called limonene. Alright, now these are the two optical isomers of limonene. One is dextro, one is levo. The dextro-rotatory isomer has got the fragrance of an orange, whereas the levo-rotatory isomer has got the fragrance of a citrus fruit, a lemon. Alright, so although they have the same structure, etc., but they differ in their physiological activities. Okay, so that's about racemic mixture. Now, we have to be aware of a few terminologies before we start discussing the stereochemistry of SN reactions. The first terminology is retention of configuration. Okay, what do we mean by that? I'll take an example of carbon. Okay, now this carbon is a chiral carbon. Alright, it is a chiral carbon. Now one of the bonds is attached to CH2OH. The others are bonded to, say, CH3. Now this is a hydrogen and this is a C2H5. Now this is a chiral carbon. Okay, this is a chiral carbon. Alright, now when this chiral compound is subjected to a reaction with, say, HCl, what happens is the OH will be replaced by chlorine. So what is the product we get? We get the product as CH2Cl, okay, and the other is CH3, CH and C2H5. So what has happened here is the bond between the carbon, asymmetric carbon, the bond, any of the bonds attached to asymmetric carbon is not broken. The bond which is broken is this COH bond, CO bond, and this is not an asymmetric carbon. So when the bonds around an asymmetric carbon are not broken, the OH is replaced by the other group, chlorine, without any change in the spatial arrangement. Right? Now this is referred to as retention of configuration. Alright? But when the bonds attached to a chiral carbon, asymmetric carbon atom is broken, it can undergo inversion, retention and racemization as illustrated here. Okay, now look at this compound. This is a chiral carbon. The central carbon atom is chiral because it is bonded to 4 different groups. You look at the group X. This group X, okay, the CX bond is being broken. So when the CX bond is being broken, there are 3 possibilities which can arise. One is the incoming group Y can replace X and the configuration is retained and the arrangement is retained. So this is retention. This is retention of configuration. Another possibility is the configuration can be inverted. You notice that X was on the left. The Y has got attached on the opposite side. So this has undergone inversion of configuration. Inversion of configuration. Another possibility is you can also arrive at a racemic mixture. 50% of, when you react with Y, X is replaced by Y to get 50% of this isomer and 50% of this isomer. Both are non-superimposable mirror images of one another, and you arrive at a racemic mixture. So what you've got to understand is, if the bond on a asymmetric carbon atom is broken, it can undergo inversion, retention or racemization. So this was part 1 where we discussed the basics of optical isomerism. Please watch the next video on part 2 where we will discuss the stereochemistry of SN reactions. Thank you.